everybody, welcome to the Big Dog Festival. Apparently I am live now. Yes, I can see myself coming out there. My name is Marty Jopson, and this is a show all about electricity, which is why I like to call it ZAP, because hopefully that's not what is going to happen. So let's start by making some electricity. So I'm going to move to a different camera so we can sort of see me a bit closer. There you go. So here am I. So let's make some electricity. I need one of these. This is a piece of plastic pipe. You can see it's a hollow pipe. Ooh, you can see down it there just about. From B&Q actually. And this is a piece of fake fur. And all you need to do to make electricity is this. There you go. That was pretty boring, I think you'll admit. But you can make electricity really, really easily. Every time, oh, hold on, my phone's just gone off. Every time you sit down and wriggle your bum in the car, for example, you make electricity. And all you need to do is rub two non-conductors together like this. So remember, electricity, let's just jump back a little bit. Everything in the world is made of atoms, okay? Atoms are small, tiny little globules of stuff, everything. This desk, me, you, the air in between the camera and my face, everything is made of atoms, but atoms are made of smaller things. And one of the smaller things that atoms are made of is a thing called an electron. And it's electrons that make electricity. And when you take two non-conductors, which means that electrons can't move in them, and you rub them together like that, can you hear that if I hold it near my microphone? Can you hear that sort of click, 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 click noise? And you get the same thing when you take your jumpers off from school. You know, you have those sort of, they're usually polyester or something like that, polyester jumpers, and you pull them off and you hear a kind of a clickety click, click, click. That is electricity. Now, this is my favorite demo to do with electricity because it's really lovely. So we'll go back to this camera here. And what's actually, and what I've got here is a tiny little piece of, actually, no, let's go to this camera, a tiny little piece of sort of tinsel stuff, silver foil, right? And what we're going to do is we're going to make a bunch of electricity on this wand here, this piece of plastic pipe, by just rubbing it. And all I'm doing at the moment is I'm rubbing electrons from one thing, this, to the other thing, this. And now that I've built up loads of electrons on this piece of plastic pipe, all I need to do is pick up this piece of foil here and drop it onto the pipe, and it floats. Look at that. It's like magic. No, there's no magic. I'm going to come forward so you can see it. Can you see that? I have to try and keep it right in my, so it doesn't go out of shot. There you go. There. And I can, and we'll move back a little bit. Now you know what you're looking at. Can you see that floating in the air? Yes, it's like magic. It's not magic at all. It's science. It's very simple science, because you see, the thing is, that little floaty thing there is, and what I can do is, let's see, I'll sort of push it up like that and then let it drop and catch it, and let it drop and catch it, and let it do that. And I can just keep doing this, and you can keep doing this for quite a while. What happens is when you drop that onto the plastic wand, a bunch of those electrons rush onto it, because that thing there is made of metal, and metals conduct electricity. But the thing is, electrons, oh, it's run out of juice. Electrons are like, well, they're like small children. They're repulsive. They repel against each other. So they push against each other. I don't mean it. Children aren't repulsive at all. I love them. They're lovely. They repel against each other, and the electrons that are on here push against the electrons that are on the little floaty thing, and it pushes it into the air. So it floats up into the air. Now, I'm going to pop that down there like that. Get rid of that carefully like that. And put that there like that. Because, okay, so that's a very easy way to make electrons. And when you get out of the car or you pull your jumper off, you make electrons. You rub electrons. We don't make electrons, but you rub them from one surface to another. And that is called static electricity. Okay, now we can make static electricity. There's lots of ways to make static electricity. And by the way, if you have any questions, you can just send them by email, or you can post them in the chat there's a sort of a chat thing on the side if you're watching this on YouTube. And they usually, every now and then, they'll sort of scroll that across underneath down there, just down there, so you can see the email. So teachers, if you're watching, just send us your questions. And then what we'll do is at the end, I will try and answer any questions you have about me, about what I'm saying, or about science in general, because I'm happy to tackle anything. So, okay, this is one way to make electricity, but it's a pretty slow and laborious way, and you don't actually get very much electricity from it. You don't move many electrons. What we need to do is we need a machine that will do that for us. And this under here, under this massive silver cloth here, it's sort of silver ghosty, is a static electricity machine. I like to call it the beast, not because it's so big, although it is quite big, but because it's a really, really difficult machine to use because it's very temperamental. So let's see if the beast is going to work for us. Here it is. Dun, 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 dun. There is the beast. Now, the beast is a type of machine called a Van de Graaff generator. It was invented by a guy called Van de Graaff. He's an American guy. Anyway, and basically what it does is it does this. It's just a machine to do that. And it doesn't sort of rub it like this. It rubs it, it rotates it like that. So it rolls it. So there are rollers at the bottom and rollers at the top. And what this does is this takes electrons, okay, and it moves them from the bottom to the top to this big metal globe at the top. And they pile up on here. And then what happens is I can make those electrons jump through the air. And when they jump through the air, we get a spark. And I can make a spark that will jump from there to my, this is called a discharge wand. So what we'll do is I'm going to try and show you this on this camera here. So I'll do that. So if I press that button there, it's not working. Why is it not working? Let me jump back to this. And I have to press that button there. Okay, let's do that. So I shall press that button there. Right, okay. And hopefully you can now see this camera here. So I've got a little camera here. We're going to point this camera at that there, like that. And then we're going to try and arrange it so that you can still see me in the corner. So here am I in the corner, and there's our big ball there, right? And I'm going to try and make a spark here. And we'll see if we can see this spark. Now, there are problems to do with how this works, which I will explain in a second. But let's just have a go. So I'm going to charge it up, get going with the spark, and I'll tell you how much electricity this generates. We can measure electricity in a couple of different ways. One of them is called something called voltage, and the other is something called current. I'll talk about those in a little bit. But this machine, generally speaking, most of the kit you use uses maybe 5, 6, 7, 8, 12 volts. This machine makes 300,000 volts. So it's quite dangerous. Here we go, charging it up. Let's see if we can get a nice big spark. See a spark. Oh. Now, did you see the camera that you saw my face on disappeared? There it goes black. And it's actually really difficult to see the sparks. And every time I do, it knocks out the camera. The sparks are, I can see them, and it's quite difficult to. And the problem is, okay, there's a lot of problems to do with this. I'll come to this camera here. The problem is that the sparks are so quick that the camera doesn't see them. Your eyes can see them, but the cameras don't see them. And the other thing is that camera over there, this one here, this one over here, this camera in the corner, every time you get a spark, the spark knocks out the camera. It's something called an EMP pulse, but don't worry about that too much. So what we can do, though, is rather than just, I can't really show you the spark, but I can show you what the spark can do. So I've got here a whole load of pie dishes. Where are you? There you are. Okay, pie dishes here. Okay, this is from me eating mince pies at Christmas. Yeah, I ate a lot of mince pies. So what we're going to do is we're going to put these pie dishes on here, like that, right? So they're up on the top there. And then what we'll do is we'll turn on the machine and we'll see what happens. And what we'll do is, remember, all those electrons fly up to the top, okay? And when they go up to the top, and remember, electrons don't like each other. They push away from each other. So let's see what that does. Here we go. 3, 2, 1. fly in the air. And we make a horrible mess, and I scatter electrons, pie dishes all over the place. Should we try some bigger ones? Here's some bigger pie dishes. These are from meat pies. Yum, 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 yum. We'll put those on top, and we'll see. And we'll see if these will work as well. Because what's happening, think about it. I'm just going to move some of these pie dishes out of the way, because otherwise I tend to slip on them. What happens is you have two pie dishes like this. Where are you? There you are. And when they get covered in electrons, the electrons push against each other. So the electrons that are on the top pie dish push against the electrons that are on the bottom pie dish. And just like the little piece of floaty stuff here, okay, the floaty stuff, the electrons push the pie dish up into the air, and then it flies off, and then the next one goes, and then the next one, and the next one. But the question is it strong enough to move the big pie dishes? Sometimes it works, sometimes it doesn't. We shall give it a go. Here we go. 3, 2, 1, pie dish! Come on, come on, come on. Yes, yes! Unmute. Can you hear me now? Can you hear me now? Can you hear me now? 1 2 1 2. Yes. What is the sound like? Is it bearable? Okay, apparently you can hear me now. I don't know if that's any good. I don't know what happened there. I suspect what happened is because I'm using the Beast. The Beast messes around. You saw how it messed up with the cameras. It messes around with the sound as well. I'm really going to have to do something about that. Anyway, right. So back in the game. Right. What we should do now, let me just see. So now I've slightly lost my place. So let me see. How am I doing for time? Okay. Let's have a look. Is this working here? Yes, that is working there. Okay. So let me get rid of this and go back to this. So what we're going to do now, though, is we can make all this static electricity and I can mess around with that. But what I want to do now, let's see, how much time have I got? Is I want to talk about how we get electricity, because we don't generally get electricity using static electricity, okay? Because it's not very useful. The way most of us get electricity is using things like this, okay? A battery, obviously, because most of us get our electricity from batteries. A lot of my kit that I'm using now uses batteries. So what we need to do is I want to talk to you about how the battery was invented. Let me show you how the battery was invented. So here's my little camera here onto the table again. Let's move all that out of the way. And I'm going to tell you a story. I'm going to tell you a story that doesn't involve a lemon and doesn't involve any of this kit, but does involve a gentleman called Luigi Galvani. And what Luigi Galvani did is Luigi Galvani realized that when you put two different metals together with an acid, things happen that you might not expect to happen. Now, this machine here, this red thing here, is what is known as a voltmeter. And a voltmeter tells me how many volts I've got. And if I take a battery like this and I attach it to the voltmeter like this, I put one end on the positive and one end on the negative, it tells me that I have 1.5. There's a decimal point there. So it's 1.5 volts, 1.5 volts. That's what you get from one of these batteries here, okay? Remember, that machine over there, 300,000 volts. So what we want to do, though, is I wanted to show you how you made a battery. And all you need are two metals. Here's a piece of metal. It's a piece of a metal called copper, okay? And it's a kind of, you find it in a lot of pipes are made of copper. It's quite a bendy metal. It's a good metal to work with. It's also good for electricity, okay, because it moves electricity very well. So we'll take one bit of copper there, and I'm going to poke this piece of copper metal into my lemon here, like that. And then I'm going to take another thing, which is this nail here. And this nail is coated with a different metal called zinc. And I'm going to push that in as well, like that. So they're not touching, but there is liquid inside this lemon, and I'm sure you know that lemons have a type of liquid in them called an acid. It's why that kind of hurts if it gets into cuts. And if I now connect the positive, the red, to the copper, like that, and the negative, the black, to the nail, which is coated in zinc, look what happens. I get a voltage. I get about 0.6 volts. So it's not quite as much as this. It's about a third what this is, but it's still a voltage. So I've just made a battery with a lemon, and there's nothing more to it than that. It's just a bit of chemistry going on in here, okay? And the chemistry is basically a promise of electricity. That's what it is. It's a promise that you'll have electricity when you need it. Oh, it's fallen off. There we go. Clip it back on. Now, I can prove to you that it's just chemistry, because if I take another piece of metal here, there, okay, this is a different type of metal. It's a type of metal called magnesium, and it's much more reactive, so it does a lot more things. It's quite difficult to get hold of. We'll take out the zinc, and I'll put in its stead a piece of magnesium. And now look what happens. We get as much voltage as we did with one of these batteries. So with a lemon, I can make as much voltage as this thing here. Okay, so it's an astonishing thing when you realize it, that all that the battery is doing is it's just a bit of chemistry. And the thing is, the chemistry stops as soon as you detach it, and it just sits there. So here's the question. Why don't we just use lemons? Why do we use batteries? Now, the reason behind that is because of what the two things that I've mentioned already. Now, you remember I said that there were two ways of measuring electricity. We can measure current and we can measure voltage. Now, this is really hard stuff. So if you don't quite get it, don't worry about it too much. This is stuff that people doing GCSE and A-level don't get, quite frankly. Most grown-ups don't really get this. But, okay, here's an electron. It's not an electron. It's just a little green glowy ball. Okay. But imagine the electron is moving from here. Here it is. And it's moving across there. And oops. And I try not to drop it like that. It moves across, and imagine there's a sort of a wire here. And it moves across down the wire. And as it moves down the wire, that is what is known as a current. And a current is just the number of electrons. So if you have 2 electrons and they move, you have twice as much current. 1 electron, 2 electrons, twice as much current. Simple. So what then is voltage? Well, voltage is how much work you have to do, how hard you have to push the electrons to get from one side to the other. And if this was a wire here, a copper wire, copper allows electrons to move really easily. So it's like, you're on a playing field and there's no one in the way, and you can just run across and the electrons can zoom across. So very low voltages are needed. But if, imagine you had a playing field full of children, and I said run from one side to the other, you'd have to dodge and weave and duck and dive, and it would be more difficult, and you'd have to do, it would take more work, more energy to get across. That's voltage. So voltage is how much work you have to do to go from point A to point B, and current is how many electrons go from point A to point B. So it's a subtle but really important difference. Now, I'm going to move on to one other type of electricity. And before we go on, I'm just going to remember any questions. If you've got any questions, any questions? Oh, apparently I've been asked to give a shout out to Close Burn Primary. That could be a slippery slope if I start on that. We will ask, there's some more questions coming in. Excellent questions coming in. So keep posting them. I'll probably answer them at the end if we have a chance. Because there's one more thing I wanted to show you. Now, first of all, a warning. Do not mess with electricity. It is very dangerous. If you get too many electrons passing through you, they will kill you, okay? There's lots of reasons why they can kill you. I don't have time to go into that, but electricity is super dangerous. Now, the electricity you get from a battery is relatively safe, so long as they're small batteries like this. But the electricity you get from the mains, and what do I mean by mains? Well, you have electrical sockets all around your homes and all around your school. And I'm sure you've been told never to poke anything in those sockets. And the reason for that is because if you do, you will allow the electricity to come out and into you, and that's the end of you, basically. You're toast, quite literally toast. That will kill you. But what you can do, if you know what you're doing, is you can use that sort of electricity, which is a different kind of electricity, and you can turn it up to 1,000,000 volts, which makes it really dangerous. And that's what I've got over here. I'm going to show you another piece of kit over here. This machine here is called a Tesla coil. And a Tesla coil uses mains electricity and turns it up to 1,000,000 volts. So would you like to see a massive spark? Of course you'd like to see a massive spark. I'm going to turn off some lighting, that one and that one. And then I'm going to put on a set of headphones because this is very loud as well. And let's see if we can see a really big spark, 1,000,000 volt spark, okay? So here we go, a big spark, which you can't see. And the reason you can't see it is because there's only 1 spark a second. What we need are more sparks. How about 1,000 sparks a second? Well, okay, so what you heard there, though, was you heard the sparks. And every time you hear a spark, it's actually what's known as a sonic boom. And a sonic boom hits your ear and you get a pulse. But if you have enough sonic booms a second, you get a tone, you get a note. And what that means is that you can do something very clever if you know what you're doing. And remember, electricity's dangerous, kids. Don't play with it. What we can do, well, let me just show you, because this is kind of cool. So I have to just get myself set up right. How about this? Oops, wrong button. Doctor Who theme, obviously. That was quite good. I quite like this one. That's sort of magical. You know what that one was? Harry Potter, obviously. But what could possibly be better than 1 million volt spark? Well, clearly 2 million volt sparks, which is why, and I'm just going to step over here now. Over here, I have my second Tesla coil. Bum, 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 bum. Let's plug this in and turn her on. And then what I need to do is I need to connect my 2 Tesla coils together with my machine here, which is a little bit fiddly, but we can do that there like that. And then, hopefully, everything's plugged in. I return to here. And now what we can do, I'll turn on the different Tesla coils. Both Tesla coils turned on. Let's choose the right mode. All right, that's that, that's that. And what we're going to do is, here's a little tune for you. Hopefully this will work. This is a new piece of kit for me, bit of a new thing. Here we go. This is completely awesome. No, that didn't work. Right, let's try it this way. Oh, everything is awesome indeed. Okay, and that's knocked out that camera. Will it come back? Oh, no, it's not going to come back. We're going to have to use this camera. Oh, I've got camera problems. Camera problems. There we go. So let's try. I'm going to try one more. I'm going to try this one here. This is, technically, this is a Polish folk song. Oh, yes, indeed. Right, turn everything off. And now I need to just quickly turn that off, turn those on, and run over here and turn that off to make it safe. And then I'll come back here, and then we'll just go back to that camera there. And that, ladies and gentlemen, is ZAP. Some experiments using some of the best and most powerful electrical experiments you're likely to see. Hundreds of thousands of volts, millions of volts indeed. Right, let's have a look at some questions. Send in your questions, let's do some questions. Right, I've got some questions here coming in. And let's have a look. How did I learn how to play music with electricity? Well, these machines over here, I built those machines quite some time ago now. Or at least I built the first one, and then I built the second one. It's quite difficult. Making Tesla coils, it's something I've done before, many years ago, and for a television program. And I thought it'd be quite fun to have some, so I could show people what you can do with a Tesla coil. So how did I learn to do it? I taught myself. What's my favourite question, says Sam. What's my favourite experiment, says Sam. You know what? Of these, my favourite experiment is this thing with the floaty. Okay, I just love that. It's so simple. It's so surprising. When you see it, it's quite, it's quite difficult. I'm doing this on a camera. I'm in Yorkshire, you're in Scotland. It's difficult, and I try to show you this as best I can. But when you see it for real, it really is quite surprising. I love that, and it's good fun to do as well. Okay, Aaron, have you ever done an experiment that's gone badly wrong? Good question. Well, sometimes my experiments go wrong. We've had a few things go wrong today. So far today, the fire alarm was going when I got here, and that took me half an hour to turn off. My boiler broke down, and I'm getting somebody keeps ringing me to fix my boiler on my phone at the same time. My earphones have gone. One of my cameras has gone now. So sometimes the technology breaks. Generally speaking, my experiments, because I practice them, they work. Sometimes they don't work. But you try not to do things that don't work. But has anything ever gone badly wrong? Not really. I've never done an experiment that's gone badly wrong. Sometimes they just don't work, and it's just a bit, that was rubbish. It doesn't go bang, It's just a bit boring. But they've never gone badly wrong. No one's ever been hurt, put it that way. So, what sparked? Mia says, what sparked your interest? Haha, see what you did there, Mia. Very good. In science, is there a good kit I can get for home to learn more? Right. What sparked my curiosity about science? Actually, it was my grandparents, my grandfather in particular, who used to send me books all the time about science and technology and experiments and machines and things like that. And then I lived originally, I grew up in London, and my dad used to take me to the Science Museum. All my family are linguists, so they're all people who speak foreign languages. So my dad was a teacher of languages. And but even so, they used to take me up to the Science Museum, and I just loved it. I always have. And what's a good kit that you could take home? Well, I'm always a bit on kits. Because the trouble with kits is invariably they're just a bit rubbish. Okay, what's better? What's better than a kit is for you to start experimenting. There's so much information out there. Go to your local science centres when you can. Look at resources online. Big Dog and stuff like that. I'm sure they've got stuff on there. Look at books that have got, kind of experiments in them, and then try those. I think those are usually much better than a kit, because all the kits do is they just take things that you can buy anyway, stuff you can buy in like, Sainsbury's or Tesco's, and they put them in a box, and then you buy them, and you pay more than you would have if you just gone to Tesco's and bought them there. So the best thing to do is to find really good books. There's a really good science book. I'm going to a little advice on the science book by a guy called Alom Shahar, spelled S-H-A-H-A, Alom, spelled A-L-O-M, Alom Shahar, and he's an old mate of mine, and he did a really good science experiments book for at home. I don't have any more details for that. If you just type into Amazon, Alom Shahar, he's done a few books. And one of them is obviously the experiment book. So there you go. Joyce is asking, did you love science at school? Yes, I did. I loved doing science at school. I was the science nerd at school. I did. When I got to A-levels, I did maths, physics, chemistry, and biology. And then I went off and I did science at university. And then I went off and did more science. And I have a PhD, a doctor. I'm a doctor of science. So I've always loved doing science. And yes, school was very important for me for science, because it allowed me to sort of see all the different bits of science. And as you go further up in school, you'll get to do more and more interesting science. And that's when it gets really good. So let's have a look. What else is here? So, okay, there's a question from Close Burn Primary. How do you make music with electricity? Okay, so this is a very specific question. So, okay, let's see if we can go back to this camera here. Is it working? Oh. So these machines here, right? Actually, let's bring one over. Let's see if I can unplug one. They should be all right now to mess about with. Bring it over so you can see what it's like. It gets quite warm, and there are a few things you have to watch out for when you handle it. But here it is. So there it is. There's a Tesla coil, invented by a guy called Nikola Tesla. And what happens, right, is you have here, just there, just in that black bit there are a series of rings of metal, a coil of metal that goes a spiral. And this bit here looks like copper. It looks like just a big copper tube, but it's not. It's actually thousands and thousands and thousands of coils of very, very fine wire. And what happens is you push electricity into this coil, and you push it in from mains electricity. It's 240 volts. And what this does is this then uses magnetism as well to create 1,000,000 volts. And that 1,000,000 volts then makes a spark, which comes out. Bzz. And that spark heats the air to hotter than the surface of the sun, tens of thousands of degrees. And as it does that, the air expands, boom, and creates what's known as a shock wave. And that shock wave hits your ear, and you hear a click. Now, if you hit your ear with a shock wave once, you hear click. But if you hit your ear with a shock wave 50 times a second, you don't hear click. What you hear is a very low note. And if you then go up all the way to 1,000 clicks per second, you go, and it goes all the way up. So by changing the number of shock waves per second coming from this machine, I can create a note, just as if you were playing a piano. Ding, right? And then what I do is the computer inside my little controllers, what that does is that tells the machine how many notes, how many clicks per second, how long to do that for, and then changes and keeps going like that. So I can use it and I program it so that it plays music. Okay, the original Tesla coils invented by Tesla, Nikola Tesla. There was a really good, Doctor Who, talking of Doctor Who, in the series, the last series, where the Doctor meets Nikola Tesla. And Nikola Tesla, when he made it, it couldn't do that. But this is now a digital Tesla coil. It's a bit more complicated. So that's that. Do we have any more questions? If anyone's got any more questions about anything at all, do post them in the chat. Get your teacher, just shout them out, or maybe don't shout them out. Politely put your hand up, ask your teacher, and then put them in there, or send them apparently to questions@weektownbookfestival.com. Right, what else have we got here? I don't know whether you want me to keep talking Weektown Book Festival. Do you want to post them here? Because I think I've answered all the questions that we've got there, at least one way. What I can show you, though, is one other thing that I skipped whilst we're here. I'm going to show you how to make an electric motor. Because the thing is, batteries and magnetism, seeing as I have your attention if we're waiting, go hand in hand. Here's a battery. There's a powerful magnet at the bottom. Okay. And if you want to make an electric motor, all you need to do is take a wire and join the top to the bottom like this. And when that happens, what does that? Ta-da! How cool is that? An electric motor, invented by a guy called Michael Faraday. Here's a different one. If any more questions, do get them, keep them coming in. That's the trouble when you have powerful magnets, they jump together. Let's just break these magnets apart. You've got to keep these apart, don't they? They're too attractive to each other, unlike electrons. There we go. That one stopped. Get it going again. There it goes. And here's a slightly different model. I'll put that. There we go. That. Called homopolar motors. And if you want to know, you can look them up on the internet. Homopolar motors, simple electric motors. Right, okay. Wigtown Book Festival. Can you tell me what you would like me to do? Do you want me to keep talking? Should we draw this to a close? We are good to wrap up, it says. So what I'm going to say is, I'm going to come back to that. I'm going to say thank you very much. Sorry I had a few technical problems. We got there in the end. That's the problem when you mess about with high voltage electricity. It does horrible things to electrical equipment. But thank you very much for watching. My name's been Marty Jopson, and you've been very lovely. Have a nice day. Bye-bye.